In the last two sections, we studied electrophilic aromatic substitution reactions. Aromatic compounds can also undergo other reactions. This includes nucleophilic aromatic substitution reactions, reactions involving benzene, oxidation of aromatic compounds, bromination of alkyl benzene side chains, and reduction of aromatic compounds. In this section, we are going to look at a few simple ones. When an alkyl group is attached to a benzene ring, the carbon directly attached to the benzene ring is called benzylic. Okay, benzylic carbon has a special reactivity. When potassium permanganate is added to the compound, the bond between this benzylic carbon and a neighboring carbon break, and 2 oxygen is added to form benzoic acid. This reaction is called oxidation reaction because oxygen is added to the product. In organic chemistry, oxidation reaction refers to the reaction that adds oxygen to the organic compound, or on the opposite side, hydrogen is removed to the compound, also called oxidation reaction. Potassium permanganate is a strong oxidizing reagent, which is suggested by the formula, has 4 oxygens in it. So in general, when an aromatic compound here, Ar means benzene ring, has an alkyl group, R is an alkyl group, and no matter how complex this alkyl group is, when potassium permanganate is added, this bond between benzylic carbon and a neighboring carbon break, oxygen is added, product is benzoic acid. Okay, note that benzylic carbon still remains. Only alkyl side chain are oxidized. The side chain must have a benzylic carbon with a hydrogen. So this hydrogen is needed for the reaction to proceed. And strong oxidizing reagents are needed. Potassium permanganate is one of them. Another one is sodium chromate. And you can see they all have many oxygens in the formula. This reaction does not occur. This is because the benzylic carbon has no hydrogen. So even though potassium permanganate is added, there's no reaction. In the last slide, we mentioned that adding oxygen to an organic compound is an oxidation reaction. Adding hydrogen then is a reduction reaction. So in this example, the double bond can be reduced to alkane by adding hydrogen gas when palladium is used as a catalyst. And note that the benzene ring is untouched. The reaction only occurs to the double bonds. Now, when a carbonyl group is directly attached to benzene, this is a benzylic carbonyl group. And benzylic carbonyl group can also be reduced by hydrogen gas with palladium as a catalyst, forms alkyl group. So acetophenol is converted to ethylbenzene. Okay, ethylbenzene. So interesting thing in this reaction is the acetyl group is a metal director, and alkyl group is a ortho-para director. And this has an importance in organic synthesis. Okay, for example, how do you make this compound? You have alkyl group and the sulfonic acid on the metal position. So if you have alkyl group, then sulfonation can only take place on this ortho and the para, not the metal position. All right. So how do you do this reaction? Okay, this reaction suggests that we can start with this acetophenol. Okay, because it's a metal position, so we can add this sulfonic acid here in the metal position, and then we perform the reduction reaction to reduce the ketone or CO double bond into CH alkyl group, and then here we're metal position. Then we have SO3H sulfonic acid. Okay. The reactions mentioned above has other advantages. For example, if we perform Friedcraft alkylation using chloropropane, okay, the product will be propylbenzene. All right, and due to the rearrangement, remember the cation rearrangement forms more stable carbon cation, so we also make isopropylbenzene. So the product is a mixture of these two. All right, but if we perform Friedcraft acylation reaction, okay, we get a compound with benzylic carbonyl, and then we perform hydrogenation or reduction reaction, and we also get propylbenzene. So if propylbenzene is our desired product, this second method gives you 100%, no other side reactions. On the other hand, if you use the first method, the Friedcraft alkylation reaction, we get a mixture. Only part of the reactants becomes the desired product. The hydrogenation reaction not only reduce benzylic carbonyl, but also reduce other functional group, including NO2 nitro group. So the product is a ethyl benzene with an amine, okay, because NO2 is reduced. So the product is actually an anilide. Before synthesizing polysubstituted benzenes, planning and consideration of alternative routes are needed. The ability to plan a sequence of reactions in right order is valuable to synthesis of substituted aromatic rings. Example: how do we add 3 substituents to benzene ring? Chlorine, propyl, and sulfonic acid. Note that chlorine is a ortho-para director. So if we add the chlorine first, then the propyl will go to this position, and this doesn't work. Propyl is also ortho-para. So if we add the propyl, then chlorine doesn't work. Okay? Sulfonic acid is a meta director, so you cannot add chlorine to the para position. In addition, this is a very strong electron withdrawing group, and Friedcraft alkylation will fail. All right, so how do we perform this reaction? In this case, we think about the method we just learned to convert a meta director to a ortho-para director first. So we add Friedcraft acylation reaction. Okay. So first perform Friedcraft acylation. We add this ketone group so that it's a meta director. And next step, we can add chlorine to the meta position. Okay. So these are meta position, and then this one we need to change to propyl. And we perform reduction reaction. So hydrogen gas, palladium, and that will install 2 desired functional group in the right position, okay, as in the product. So the third one is sulfonation reaction, because this is a activator and also ortho-para. So this will go to here, and that gives you the desired product. Homework: please work on problems 16.18 and then 16.21 to 16.23. Also work on some other additional problems in the textbook.